Hello everyone, welcome to the Internship Studios first session of our module number 2, which is AWS databases. So we'll be covering primarily RDS, which is the Amazon Relational Database System. We will be covering the Amazon Aurora and the DynamoDB here. So AWS has a lot of database services to meet the various different application requirements. At the forefront of it, we have the Amazon RDS. Next, we have the DynamoDB. We have Amazon Redshift, which is a fully managed data warehousing service. We also have Amazon DocumentDB, which is a NoSQL based document database service. We also have Amazon Neptune, we have Amazon Elasticache, we have Amazon Aurora, we have Amazon TimeStream, we have Amazon QLDB, and we have Amazon key spaces. So we have a whole lot of database services. But at the core of AWS, we have RDS and the DynamoDB, which are frequently asked in the examination questions, which are AWS Solution Architect Associate, or in the industry also. Most people and companies are using these services. So I have selected these services to be discussed, and will also be having the hands-on sessions here. So we'll move to the first slide here. The first question that will come up to our mind is, what is a database? So we have the definition. A database is an organized collection of structured information or data typically stored electronically in a computer system. A database is usually controlled by a database management system. Let's imagine and compare it along with an analogy. So let's imagine a very busy library for understanding what a database is in the context of a real world story. So here our library serves as a hub of knowledge, much like a database is a repository of information in the digital world. So the librarian we have who controls the library is akin to a database administrator who is managing and organizing the vast collection of books, just as a database administrator oversees the structured storage of data. So in that library, each book represents a record in the database. Just as a book contains various pieces of information such as the title, author, and content, a database record holds different attributes or fields. For instance, in a customer database, a record might include a customer's name, contact details, and purchase history. Now consider the library's catalog system has an index. The catalog allows patrons who are like the subscribers of the library, we can say, to quickly find books based on specific criteria like the author's name or the genre of the book or the category of the book, you can say. So similarly, in a database index, the index enables swift retrieval of data by creating organized references to information, enhancing the efficiency of the queries. Queries means fetching the data from the respective database. Now imagine a scenario where a new book arrives at the library. So the librarian, being diligent, updates the catalog and allocates a specific location for the book on the shelf. Likewise, in a database, when new data is added, the database management system ensures it is properly organized and can be efficiently retrieved when needed. So as patrons or subscribers we can say, they borrow and return the books. The librarian updates the records in the library system. If someone checks out a book, it is marked as unavailable until it is returned. So this real-time tracking mirrors the concept of the database transactions, where changes are made to the data in a way that ensures that the data main remains consistent. So in our library analogy that we have took now, so also imagine a researcher who wants to study the history of ancient civilizations. They approach the librarian asking for recommendations. The librarian, well versed in the catalog system, quickly identifies relevant books on history, archaeology, and anthropology. So, this showcases the power of a well organized database where complex queries can efficiently retrieve specific sets of data. Now, think about the library's backup system as well. So, to prevent loss of information in case of unforeseen events like a fire in the building or a flood across the city, the librarian can also keep copies of important books and documents in a very secure location. Similarly, in the digital realm, databases often have backup and recovery mechanisms to safeguard against the data loss. So, as we have just saw the library analogy, a database is nothing like a well maintained and organized library. It stores and manages information systematically. It allows for efficient retrieval through indexing. It ensures the data consistency through the transactions. Also, it incorporates the backup systems for the data protection. So, in both worlds, the goal is to provide users with very easy access to the information they need while maintaining the integrity and security of the stored data. This was about the definition of the database. Coming to introduction to the AWS databases. So AWS has around most of the popular database services. We have the Amazon Aurora. These are all the logo of the respective database systems. We have Amazon Aurora, Amazon Redshift, Amazon DynamoDB, Amazon Elasticache, Amazon DocumentDB, Amazon Keyspaces, Amazon Neptune, Amazon TimeStream, and Amazon Quantum Ledger database. So initially we have the Amazon Aurora. So it is a MySQL and PostgreSQL compatible relational database engine. It combines the performance and availability of high-end commercial databases with the simplicity and cost effectiveness of open source databases. Open source means which are freely available. Next we have the Amazon Redshift. It is a fully managed data warehousing service. It is designed for the analyzing large datasets using SQL queries. It also offers very fast query performance and the ability to scale storage and compute resources. Next we have the DynamoDB here. So it's a fully managed NoSQL database service. It is also designed for high performance applications with very low latency requirements. It also supports both document and key value data models. Next we have the Amazon Elasticache. It is also fully managed in-memory data store and cache service. It supports popular caching engines like Redis and Memcached. It improves application performance by reducing the latency and increasing the throughput. We have the Amazon DocumentDB. So it's a fully managed NoSQL document database service compatible with the MongoDB. It also provides the scalability and flexibility of NoSQL databases with the benefits of a fully managed service. We have the Amazon key spaces, especially we use this service for the Apache Cassandra, which is another database. So it is a key spaces is also fully managed, scalable and highly available Apache Cassandra compatible database service. It is also suitable for applications that require a wide column store NoSQL database. We have the Amazon Neptune. It is a managed graph database service designed for building applications that work with highly connected datasets such as social networks and recommendation engines. It supports both Gremlin and SparkQL query languages. We have the Amazon TimeStream. It's a MySQL and PostgreSQL compatible relational database engine. Uh, and it, it supports as a fully managed serverless time series database. It is optimized for storing and querying time series data generated by the IoT devices, you mean the Internet of Things devices, the applications and operation logs. Finally, we have the Amazon Quantum Ledger database. So it's a fully managed ledger database that provides a transparent, immutable and cryptographically verifiable transaction log. Mostly in the blockchain technology we can see this type of database is used. It is suitable for applications that require an authoritative and tamper resistant record of transactions. So this was about a general overview of the available databases in AWS. So coming to the workflow of a database management system. So before going to the advanced concepts and hands-on, we need to know how a database management system workflow is actually working in the backend. Actually at the backend, which is managing the database, is a database management system. It's a very crucial component in managing and organizing large volumes of data efficiently. So the design and functionality of a DBMS involves several levels, each serving a very specific purpose. The three main levels of a DBMS architecture are the external level, which is at here, the conceptual level and the internal level. So these levels are interconnected through logical and physical schema, which define the overall structure and organization of the database. So in this explanation, we'll explore each level, which is schema and the real world examples. First, we have the external level, which is also known as the user view or user schema, we can say. So it is concerned with how data is presented to different users or groups of users. It allows users to interact with the database without being concerned with the underlying database structure. So this level focuses on creating a user-friendly interface tailored to the specific needs of different users or applications. So let's take a real world example. So we can consider a university database. University is like where students are studying. So the external level for students might display information about the courses, grades and schedules offered in that university. Faculty members, on the other hand, might have a different external view that includes details about the class rotors, means the classroom details we can say, the research projects that are being undertaken and the grading of those projects. So the external we can say it ensures that each user group sees only the information relevant to their role. So in a university you can say the teacher or the faculty has their own information relevant which is seen, and the students will have the student related information. So it is about the external level. So the next step we have is the conceptual level. So it is also known as the logical schema. It represents the overall structure of the database. It includes the relationships among the data. It serves as an abstraction layer that defines the data model, the constraints, and the integrity rules. So the conceptual level, we can say, it provides a unified view of the entire database system, independent of how data is stored or accessed. So coming to like a real world example, let's take the example of a hospital database. So the conceptual level might include entities such as patients, doctors, and their respective medical records. So the relationships between these entities, such as a patient being assigned to a specific doctor or having multiple medical records, are defined at the conceptual level. So this level ensures that the database is designed to reflect the real world relationships between different entities. Coming to the last level, which we have is the internal level. So the internal level, also known as the physical schema, you can say, it deals with the way data is stored, indexed, and retrieved at the lowest level of the system. So it is concerned with optimizing performance, storage structures, and access paths to ensure efficient data processing. The internal level translates the logical schema into a format that the computer system can understand and manage. So coming to the taking the example of a hospital database again. So the internal level would involve details about how patient records are stored on disk, the data storage format, and indexing structures. It might specify whether data is stored in a relational database, a NoSQL database, or a combination of both, you can say. So the internal level is very crucial for database administrators and system architects to optimize performance and storage. So you can also see the both schemas here. The first schema we have is the logical schema. So it acts as a bridge between the conceptual and the internal levels, we can say. So it defines the organization of data in the database, specifying tables, relationships, and constants. So we can see logical schema provides a very high level view of how data is structured and related within the database. So another reason real world example I can give is a, you can say, a retail business. Retail is like some kind of a shopping kind of platform. So the logical schema here might include tables for customers, orders, products, and payments. So relationships between these tables, such as a customer making multiple orders or an order containing multiple products, are defined at the logical schema level. So actually this abstraction, what it does is, abstraction means taking off that layer. So it allows developers to work with the simplified representation of the database structure. So another one is the physical schema. So the physical schema defines how data is stored, indexed, and accessed at the lowest level. It involves decisions related to storage structures, file organization, indexing methods, and data compression. So the physical schema is concerned with the optimizing of data retrieval and storage efficiency. So coming to another real world example, we can say that in an e-commerce database, e-commerce is like a online application, we can say, like Flipkart or Myntra, whichever. So the physical schema might dictate the use of a specific indexing method for faster product searches or the partitioning of large tables to improve the query performance. So it could involve decisions about whether to use solid state drives or traditional hard disk drives for data storage. So the physical schema is very important here for ensuring that database operates efficiently at the hardware level. So again, let's take the glimpse of the workflow. So the workflow usually involves interactions across all these three levels, we can say. So where users interact with the external level, where the application or interface is designed based on the requirements. So the requests and operations from users are then translated into the conceptual level, where the logical schema dictates how the data is organized and related. The DBMS in turn converts these logical operations into physical operations at the internal level, where data is stored and retrieved. For example, if a user wants to retrieve information about a patient's medical history in a hospital's database, so the external level, which is our user interface here, it facilitates the respective request. The conceptual level then interprets this request in terms of the logical schema, identifying the relevant tables and relationships of that data. Then the internal level, what it will do, it will then execute the physical operations to retrieve the actual data from the storage system. Throughout this workflow, what happens is the logical and physical schemas ensure data consistency, integrity, and efficient storage and retrieval. The separation of these levels allows for flexibility in adapting to the changing user requirements without affecting overall structure and performance of the database. In summary, a well-designed DBMS architecture with external, conceptual, and internal levels, along with logical and physical schemas, provide a very structured approach to the database management. So, this separation of concerns enables efficient data organization, a very user-friendly interfaces, and optimal system performance. So, real-world examples I have given, such as like a university, hospital, or retail databases, illustrate how these concepts are applied to address the diverse needs of different organizations. So this was about the sample workflow of a DBMS. So next important thing is we need to understand the component of a database management system. So we have the generic definition. So a database management system is a software system that provides an interface for interacting with databases and managing their operations. The key components of a typical database management system include the primary one is the database here. So it says database is the actual collection of data that is organized in a structured format. It may consist of tables, rows, columns, and relationships between the tables. So first we'll read out the definitions and then we'll simply understand how the analogy works, getting an example. So next we have the DBMS engine. So the core component that manages data storage, retrieval, and manipulation. It interprets and executes queries, manages transaction, and enforces data integrity. Next we have the query processor. So this component is responsible for translating high level queries into a series of low level instructions that the DBMS engine can execute. It includes the SQL compiler, query optimizer, and query execution engine. Next we have the data definition language. So DDL is a subset of SQL, which is a structured query language that allows users to define the database structure. This includes commands such as create, alter, and drop for creating, modifying, and deleting database objects like tables, indexes, and views. So let's understand each concept with an analogy. So let's think of in the databases we know like it already has these components. So we'll take the first component, which is the database. So database is like a vast library that stores and organizes information, you can say. In a library, you have shelves filled with books, each containing the knowledge. So similarly, a database is a structured collection of data that is organized for efficient retrieval and management. Retrieval means taking out, like getting the data. So this data can range from simple text entries to complex multimedia files. So let's take an analogy. So imagine the library catalog has the database here. It again contains information about all the books, their authors, genres, and locations on the shelves. So this catalog serves as a centralized repository, much like a database that stores and manages various types of data. Next we have the DBMS engine. So the database management engine is the powerhouse behind the scenes, we can say. So it's the librarian who manages and controls access to the books in the library. So the DBMS engine handles tasks such as data storage, retrieval, security, and concurrency control. So it ensures that multiple users can access the database simultaneously without conflicts. So here we can see the DBMS engine is similar to the librarian who organizes books on the shelves, ensure that they are in good condition, and helps subscribers to find the information they need. So the librarian, which is the DBMS engine, it like acts kind of like a gatekeeper, we can say, which can allow or deny access to the library, which is a database here, based on rules and permissions. Next is the query processor. So this is like a skilled reference librarian who helps users find specific information. For example, if you go to the library, then you say that you want this book in this category. So in a database where like users communicate their information needs through queries. So the query processor interprets these queries, it optimizes them for efficient execution and retrieves the requested data from the database. So you can consider that a library visitor is asking the reference librarian for books on a particular topic. So the reference librarian is our query processor here. So what this does is it understands the request, it identifies the relevant sections of the library like tables in the database, you can say, and retrieve the books. Books in our case is the data which is matching the query. Then the query processor also ensures that the information is fetched very quickly and accurately. Next we have the data definition language. So it's like the library cataloging system. So it defines the structure of the database including tables, relationships and constraints. So DDL is used to create, modify and delete database objects. It sets the rules for how data should be organized, much like a cataloging system that categorizes books by genre, author and other criteria. So comparing this to an analogy, we can say that the library staff creating a cataloging system that outlines how books should be arranged on the shelves, specifying categories, author names and reference numbers. Similarly, DDL defines the structure of the database, outlining the tables, data types and relationships between different elements. In the library analogy, we can see that the coordination among these components become evident. So the database here is our library catalog. It is managed by the DBMS engine, which is our librarian, which controls access and ensures data integrity. So then we have the query processor, who is a very reference librarian who facilitates very efficient retrieval of information based on user queries. Then we have the DDL, which is the cataloging system, which defines the organizational structure of the library, guiding how books are categorized and accessed. So these were the four core components. Then we have the data manipulation language. We'll again go through the definition and get an analogy here as well. So DML is another subset of SQL. used to interact with the data stored in the database. So common DML commands include select, insert, update and delete. So next we have the transaction manager, which manages transactions, which are sequences of one or more SQL statements, SQL or SQL we can say, treated as a single unit of work. So transactions ensure the consistency and integrity of the database. Next we have the concurrency control manager. So it handles multiple users accessing the database simultaneously. This ensures that transactions do not interfere with each other, preventing issues such as lost updates or conflicting changes. Next we have the data integrity manager. It enforces data integrity constraints to ensure that the data in the database remains accurate and consistent. This includes enforcing primary key and foreign key relationships as well as other constraints. Next, we have the security manager, which manages user authentication and authorization, which controlling access to the database and its objects. It includes user account management, role-based access control, and auditing. So similarly, we'll see taking the analogy as a library here. So we can see that the first one, which is the data manipulation language, it is similar to the library's book checkout and return system, we can say. So the DML, in short, we can say it facilitates the interaction with the database by allowing users to insert, update, retrieve and delete data. So it is the language through which users can communicate with the database to manipulate the contents of it. So we can see in a library, the library subscribers use the checkout and return system. So in modern digital libraries, we may have this system to borrow the books, return them, or inquire about the availability of their books. So similarly, DML enables users to interact with the database here, making requests to add, modify, retrieve, or delete data. Next, we have the transaction manager. Transaction manager is like the library's circulation desk, we can say. So it oversees the borrowing and returning of the books, ensuring that transactions are carried out reliably and consistently. So transactions in the context of a database, we can say, are sequence of operations that need to be executed as a single unit. So we can imagine a library subscriber checking out multiple books. So he's taking out multiple books. So the transaction manager here, which is the circulation desk, ensures that all books are very properly processed together. So either all successfully borrowed or none at all, you can say. So similarly in a database, the transaction manager ensures that a series of operations are either completed successfully or rolled back entirely in case of the failure. So the third component we have is the concurrency control manager. So the concurrency control manager is like the library's reservation system, we can say. What it does is it coordinates access to the resources. So resources is in the library, we have the books, to prevent conflicts when multiple users try to access the same data simultaneously. So concurrency control is essential to maintain data consistency and integrity. So we can imagine that there are two library subscribers. Subscribers means who have paid the fees to access the library materials. So at single time means simultaneously they are requesting the same rare book, we can say. So they are fighting for the same book. But the concurrency control manager, we can say, as a reservation system in the library. So it ensures that only one person at a time can access that book. So it prevents the conflicts and ensures that the data remains consistent. So In a database, this manager prevents issues like data inconsistency and might arise from the concurrent access. So next we have the data integrity manager. So the data integrity manager is comparable to a library's quality control system. So it ensures that the data in the database is very accurate, consistent, and adheres to the predefined rules and constraints. So data integrity is very crucial for maintaining the reliability and trustworthiness of the information stored in the database. So we can see that we can consider a library staff member checking books for damage. So he is ensuring that pages are very nice and neat and intact, and verifying that the information matches the catalog. So the data integrity manager in terms of DBMS, what it does is it similarly checks the data in the database. It ensures that it complies with the specified rules and constraints, preventing inaccuracies or inconsistencies. Lastly, we have the security manager here. So it is like the library's access control system. So it regulates who can access the database and what actions they can perform. So security management is very critical to protect the sensitive information and ensure that only authorized users can interact with the database. So we can imagine library requiring the subscribers to show a valid library ID card before borrowing the books. So the security manager is like a security guard. So in a database system, similarly, it checks for the user credentials, ensuring that only authorized individuals have access to the data and can perform the specific operations. What it does is it safeguards the confidentiality and integrity of the stored information. So it is like a very orchestrated system, we can say. Orchestrated means well managed system. So a library user interacts with the circulation desk, which is the transaction manager, to borrow or return books. Then it checks the reservation system, which is the concurrency control manager for book availability. Then ensures the quality of the books, which is the data integrity manager, and then presents a valid library card, which is the security manager, to access the certain resources. So here what is happening is each component it is playing a very vital role in ensuring the effective and secure management of the data. So here DML is already facilitating user interactions. The transaction manager ensures reliable and consistent operations. Then we have the concurrency control manager, which prevents conflicts. Then it comes the data integrity manager that maintains data accuracy, and finally the security manager who safeguards the against the unauthorized access. So this was about all these components. Next we have the backup and recovery manager, database utilities, query optimization engine. So we'll first read out the definitions and then I'll explain according to the analogy. So the first one, backup and recovery manager, it is responsible for creating and managing database backups to prevent data loss in case of hardware failures, software errors, or other disasters. This also provides mechanisms for recovering the database to a consistent state. Next we have the database utilities, tools and utilities for database maintenance tasks such as data loading, indexing, and reorganization. Next we have the query optimization engine. So it optimizes the execution of queries to improve performance by choosing the most efficient execution plan. So we'll discuss this additional components which are again part of the DBMS. So we can say the backup and recovery manager that we have primarily is like the library's archival and restoration system. So it's responsible for creating the backups of the database to safeguard against the data loss, and it's ensuring a very smooth recovery process in case of unexpected events. So backups are like preserving the historical copies of the library's collection. So imagine the library is periodically creating copies of the catalog that is already has and storing them in a very secure archive. Archive means which is a like storing location. So in the event like there is mishappenings like fire or damage, the backup and recovery manager, which is the archival system, it ensures that the library can restore its catalog to the previous state. So it also minimizes data loss. So similarly in a database, backup and recovery manager creates and manages backups, allowing for the restoration of data to a specific point in time. So whatever like the data was available at that point of time, then the same thing will be replicated using this backup and recovery manager. Next we have the database utilities. These are like for maintenance and repair tools used in the library, you can say. So they perform tasks such as reorganizing the data, optimizing performance, and ensuring overall system health. So these utilities can help keep the database running efficiently and effectively. So think of that like a library staff member. So using tools to reorganize the shelves, so repair damaged books which have like torn pages and optimize the layout for the better accessibility. So similarly, database utilities perform tasks such as reindexing, optimizing storage and checking for data consistency. So this ensures the smooth operation of the database. So we have the query optimization engine. So it can be comparable to a library's efficient book retrieval system. So it analyzes the user queries and determines the most efficient way to fetch the requested information from the database. So this optimization process is very crucial for minimizing the response times and improving overall system performance. So you can picture a librarian efficiently navigating the library shelves to retrieve books based on a subscriber's request. Subscriber is a librarian, like library subscriber, you can say, who has taken some membership of the library. So the query optimization engine similarly analyzes the user queries. It considers various access paths and then selects the most efficient route to retrieve data from the database. So this ensures that queries are processed quickly and with minimal resource usage. So in this comprehensive system, the backup and recovery manager safeguards against the data loss by creating periodic backups. Then the database utilities maintain the health and efficiency of the database by performing the maintenance tasks. Then the query optimization engine enhances the user experience by ensuring that queries are executed in the most efficient way possible. These components also contribute to the overall robustness and efficiency of the database system. So this backup and data recovery manager, what it does is it ensures data resiliency. Database utilities maintain optimal performance and query optimization engine enhances the speed and responsiveness of the system, we can say. So in that was all about the components of the DBMS. Now we have the popular databases. So we have these popular databases for web applications. So web applications are nothing but which are accessed over the internet browser. We have this Flipkart shopping applications like Flipkart, Amazon, right? So these are the web application and all the database is handled by these companies. So these are amongst the popular components. We have the Oracle company which has this, which is a US based company. So it has a whole lot of suite of databases. Then we have the Microsoft SQL Server. SQL is short form for structured query language. Then we have the Redis from Apache company. Then we have the MongoDB. We have the Microsoft Azure. We have IBM DB. Then we have the PostgreSQL databases. Then we have the SAP HANA. So these are some popular companies. So this is the Amazon. We can say DynamoDB. So these are the logos of those popular databases. So while handling in the cloud, we'll come across a lot of these databases. So coming to the evolution of databases, like how the evolution happened, like what we have this modern databases today, how they were historically happening, what is the root of them, we can understand. So initially in the 1950s to 1960s, what we had were flat files. So early databases were simple flat files that stored data in a tabular format. So each file represented a table and records were stored in rows. So the characteristics of these flat files were they were having a very sequential structure. You mean they are organized in a sequential manner where records stored one after the other. So each record represented a complete set of data and records were read or written sequentially. So this structure made it easy to process data in a very linear fashion. Also, there were text-based format. So data in flat files were often stored in the plain text format. So fields within the records were separated by only commas or tabs. So they made it very relatively simple to parse or read the data. This text-based format actually it facilitated very easy human readability, but it lacked the structural advantages of the more upcoming complex data formats. Then they had a very limited data type because primarily it was alphanumeric. So it involved either alphabetic, you mean ABC, or numeric, which is 1, 2, 3, and numerical values. Binary data was not as commonly handled in flat files during that period. So this simplicity in data types reflected the early stages of the digital data representation. Again, what was done is there was data manipulation and management using manual processes. So programmers and data administrators had to write custom code to read, write and manipulate data within these files. So this manual handling was very labor intensive and it actually required a very deep understanding of the data structure. This was usually also used of flat files. These were used in the mainframe computers actually. So in 1950s and 1960s, these mainframe computers was very dominant at that time. So that those commonly used flat files for the data storage. So these computers were very large centralized systems that process data in a batch oriented fashion. So aligning well with the characteristics of the flat files. But also this was posing a challenge. So there was a lack of flexibility. So the rigid structure of flat files made it very challenging to accommodate changes in data structure or relationships. So over time, as the demands on data storage and processing evolved, the limitations of flat files, it became very apparent. So in the 1970s, we saw the emergence of the historical and network based databases. So we'll see what these hierarchical databases are. So some prominent characteristics of this hierarchical database model is similarly as it was like a tree like structure. So data was organized hierarchically with each record having a parent child relation as well. So in analogy we can say that you can imagine an organizational chart for a company. So if we're working in a company, we can say that the CEO at the top is like the root hierarchy. So again we have departments which are like branches and employees within the each department has the leaves. So the CEO is the ultimate parent departments are intermediate parents and employees are the children. So this hierarchical structure mirrors the relationships in a hierarchical database. Next we have the network database model. So these are like the graph like structure, and they have this record types and sets and many to many relationships. So in analogy we can say, we can consider a social network where individuals can be friends with multiple people, join various groups and participate in the different events. So in this scenario, each individual is a record, friendship or group membership is a relationship, and the entire network resembles a graph. So the network model's flexibility captures the complexity of these relationships. So earlier this hierarchical model database, it was used in the early database applications, especially in the mainframe environments. That was also well suited for the representing of organizational structures, file systems and certain business applications. Next we had the network model usage, so which was like a network databases. So that emerged as an extension of the hierarchical database, and also it provided more flexibility. So it was also suitable for the scenarios where complex relationships existed, such as in engineering and the scientific applications. Also, it was used in the early database systems like Code ASYL, which is CODASYL, which is full form of Conference on Data Systems Languages Databases. Coming to challenges and limitations that existed. So both this actually had a more complex things actually. So there wasn't much flexibility and also there was lack of the standardization. So there was not a standardized query language that time. So that made it very harder for the users to interact with the database. So actually these were very pivotal in the early development of the database systems. So uh, structure, I think in 1970, so there was some introduction by Mr. EF Cord, so where he discovered like the structured query language, when then it became the standard language for interacting with the relational databases. So then it provided a very powerful and declarative way to manage the query data. So then we have this like, as I was talking about the relational databases. So it says the advent of the relational model proposed by Edgar Cord in 1970 revolutionized the database landscape. Relational databases organize data into tables with rows and columns and introduced the SQL. So for querying, so IBM System R and later Oracle, Microsoft SQL Server and MySQL played significant roles in popularizing the relational model. So SQL become a very popular choice till today also it is existing. So it came at around that point of time. So next we had the object oriented databases in 1980s to 1990s. So as object oriented programming gained popularity, object oriented means this C language, we have C++, currently we have this Python, Golang and Java, right? These are all object oriented programming languages. So it gained popularity at that amount of time and databases began to adopt similar principles. So object oriented databases store data in the form of objects, allowing for better representation of real world entities and relationships. So examples included Gemstone and ObjectDB. So next we have the NoSQL databases. So with the rise of web applications and the need for handling large volumes of unstructured or semi-structured data, NoSQL databases emerged. So these databases deviate from the rigid structure of relational databases and include various models such as documented oriented, which is MongoDB, key value stores, Redis, column family stores, Cassandra, and graph databases, Neo4j. So we had the advent of NoSQL databases in around 2000s to 2010s. So again, like there were a couple of things. So new SQL came into existence. So new SQL databases came around from 2010. So they aim to combine best features of traditional relational databases with the scalability of NoSQL databases. So these were designed to handle large scale distributed systems while maintaining ACID. So ACID means atomicity, consistency, isolation, durability properties. So examples include the Google Spanner and CockroachDB. So next we had the graph databases from 2010s. So the increasing importance of analyzing and traversing complex relationships in data. Graph databases have gained popularity. So they are optimized for handling graph structures and used in applications like social networks and fraud detection. Neo4j is a prominent example. Next, we had the distributed databases and cloud databases. So, after we got the cloud computing, we got services like Amazon DynamoDB, Google Cloud Spanner, Azure Cosmos DB, which also provides scalable and globally distributed database solutions. And also we had the blockchain databases. So, the advent of blockchain technology introduced distributed ledger databases with features like decentralization, immutability, and transparency. So, decentralization is a core feature of the blockchain where like we have proof of zero proof technology and transparency, like each transaction is validated by multiple other uh, like what you can say participators in the chain. So blockchain databases has exemplified by Bitcoin and Ethereum, which are the two popular blockchain technologies we have currently, have found applications beyond cryptocurrencies such as supply chain management and smart contracts. So next we need to understand the type of databases. So at the forefront we have the relational databases. So relational database management systems, so RDBMS, are a type of database management system that organizes data into tables with rows and columns. So these are some key features commonly associated with RDBMS. First is the table structure. So we have the concept of tables here. Data is stored in tables which consist of rows and columns. So similar to like in Excel sheet we may have heard, right? We have rows A, B, C, and in columns. So similarly we have the rows and columns. Next we have the rows first, which is called tuples also. Each row in a table represents a record or data entity. Next we have the columns. So each column in a table represents a specific attribute of the data. Next we have the data integrity has the feature. We have primary key which uniquely identifies each record in a table. Then we have the foreign key which establishes relationships between tables, ensuring referential integrity. Also we have the ACID properties which are atomicity, consistency, isolation, and durability. So we can again take our popular library analogy here. So we can take that RDBMS, which is a relational database management system, is like a well organized library. So where data is stored in tables, offering a very structured and efficient way to management of the information. So the table structure in an RDBMS can be compared to library shelves. So each holding specific types of books, which is data. So each shelf, which in our case would be a table, has columns representing different attributes. So it's like book titles and authors. So rows in these shelves contain individual books which can be data entries. So data integrity is also an crucial part actually. It can be like the analogy, like you can say it has the accuracy and consistency of information in the library. So just as library ensures that each book is correctly categorized and information is up to date, and RDBMS also maintains data integrity by enforcing rules which can say like constraints to prevent errors, duplications, or inconsistencies in the database. So now we can see like consistency also, considering the acid properties that we have: atomicity, consistency, isolation, and durability. So has the library's reliability standards. So atomicity is like a book checkout process. So either all books are borrowed or none. So consistency ensures that library's catalog reflects the correct information at all times. Isolation allows multiple users to use the library simultaneously without affecting each other. And durability ensures that once a book is written, it stays written. So, in summary, we can say an RDBS with its table structure, data integrity measures, adherence to asset properties, operates like a meticulously organized library, providing a reliable and structured environment for efficient data management. So then we have the SQL, which is the structured language, query language for RDBMS. It is a declarative language, so users can specify what data they need, and the system determines how to retrieve it. So in a, like declarative means we should already have the set instruction already before giving it, like you already know what you want so that the system can understand and then give the information required. Then we have the query language. It is used for defining and the manipulating the data in the database. So it's the database understandable language, we can say. Query is nothing but asking a question. Then we have the normalization. So this eliminates redundancy. It ensures that data is stored efficiently by minimizing redundancy. Then we have normalization forms. It follows the normalization forms, which is first normal form, second normal form to organize data. So we have this, like, to understand first normal form, we can see that example, like it ensures that each column in a table contains atomic values. You mean the indivisible values. So it also eliminates repeating the groups of data. For example, like instead of having a single column for phone numbers containing multiple phone numbers separated by commas, we can create a new table for phone numbers with each phone number in a separate row. So in the second normal form, we can understand it builds on the first normal form and then it eliminates partial dependencies. So here all non-key attributes are fully functional, dependent on the entire primary key. For example, if we have a table with a composite primary key, for example employee ID and project ID in a company, and information like employee name depends only on employee ID, we can move employee name to a separate table. So then we have the third normal form, which is also like we can identify that as 3NF. So it builds on the second normal form and also it eliminates the transitive dependencies. So non-key attributes here also should not depend on other non-key attributes. For example, if we have a table with department and manager, where manager depends on department, we can create a new table for departments and link it with the original table. So what this normalization process helps us is, it helps us to achieve the benefits such as data integrity, efficient storage, easier maintenance, and enhanced query performance. Next we have is the feature is the data relationships. So we have joins here. It allows the combination of data from two or more tables based on related columns. Relation types include one to one to many to many relationships can be established. So that was all about the features of the RDBMS. Here we have the popular RDBMS databases, which are like Oracle. We have couple of Oracle databases. We have MySQL database. We have Microsoft SQL Server. We have the PostgreSQL database, and we have the DB2 database here. So these are some examples. Next type of database are the key value databases. So we'll first understand the definition. So key value databases are a type of NoSQL database that stores data as a collection of key value pairs. In this model, each data record is uniquely identified by a key, and the corresponding value can be a simple data type, a complex data structure, or even binary data. So key value databases are known for their simplicity, high performance, and scalability. So here are some key features and characteristics of key value databases. The first is the data model. So data model we have is the key value pairs. So each piece of data is stored as a key value pair. So where key is a unique identifier and the value is the associated data. And the next thing is the it is schemaless. So key value databases are often schemaless, allowing for flexibility in the types of data that can be stored. Next is the simplicity. It is minimalistic structure. The data model is straightforward, making key value databases easy to understand and use. Next one is the operations. So basic operations include inserting, retrieving, updating, and deleting key value pairs. So next feature is the scalability. So horizontal scaling. Key value databases are designed for horizontal scalability, allowing them to distribute data across multiple nodes to handle large amounts of data and high read and write loads. Next is also the partitioning. Data can be partitioned across multiple servers to ensure even distribution and efficient scaling. So we can imagine that we have a collection of boxes and each box has its own unique label. So label here we can take it as a key. So inside each box is something valuable or meaningful, we can say. We can take that as value. For example, box with key 123, so it has inside a red apple. Again we can say box with key 456, inside it has a small notebook. So the key here is the label on the box, value here is the content inside the box. So similarly in key value database we'll be having key has a unique identifier for the data. Next value we will be having as the actual data or information associated with that key. So these key value databases are very highly efficient for certain tasks because they provide a direct way to retrieve the information. For example, if we want to content the box of labeled which is 456, you can go straight to that box without having to search through the others. So these like in real world, these type of databases are normally used where speed is very crucial, where like retrieving data quickly is essential. Then where is simplicity involved, so the data structure is very simple and flexible schema is preferred. Next is scalability is a priority. Also we have the performance. So these key value database are very performant. Actually they have very fast read and write operations which also provide low latency. They also have in-memory storage. So some key value databases or optimized for in-memory storage, further enhancing performance. So use cases are for caching, session storage, storing session data in web applications, configuration management, storing configuration parameters for applications, then real-time analytics. So if you want to have the analytics and of a application, live application, so you can use for the logging and processing of that real-time data. For examples of key value databases, we have as Redis, which is an in-memory data store known for its speed and versatility. We have DynamoDB, which is a managed NoSQL database service provided by AWS. We have the Cassandra, which is a distributed NoSQL database that supports key value pairs as well as more complex data models. So these are some couple of examples that we saw. This is the Redis, we have the DynamoDB, Amazon, and we have the Cassandra. So coming to the AWS databases family. So here we'll be focusing on the AWS RDS. So we know that every application needs a place to store data from users, devices, and the application itself. So databases are very important backend systems that are used to store, manage, update, and analyze data for all types of applications, from small back office systems to mobile and web consumer web applications with global scale. So first we have the Amazon RDS, which is short for AWS RDS. So Amazon Relational Database Service, Amazon RDS, is a collection of managed services that makes it simple to set up, operate, and scale databases in the cloud. So we have the option to choose from 8 popular engines: Amazon Aurora PostgreSQL Compatible Edition, Amazon Aurora MySQL Compatible Edition. We have RDS for PostgreSQL. We have RDS for MySQL. We have RDS for MariaDB, RDS for SQL Server, RDS for Oracle, RDS for DB2. So we can also deploy on-premise means in our physical own data center with Amazon RDS on Amazon Outposts. So we have a feature called Outposts also, or with elevated access to the underlying operating system and database environment using Amazon RDS Custom. So we'll see how high level workflow of RDS is. So we can see that the workflow is pretty simple. Just we can go to the console of the AWS. We can connect to your application to any of the 7 Amazon RDS engines available. Then we have the Amazon Relational Database Service, which is set up, operate, and scale a relational database in the cloud with just a few clicks. Then we have all these managed features, which are security and compliance, performance and scalability, automated patching and upgrades, backup and recovery, monitoring and alerting, data durability and redundancy. And then we can just focus on the innovation. We can migrate without re-architecting apps. So we already have less time managing databases. We can improve database and infrastructure efficiency, and we can decrease the capital and the operational expenses. So we can see in the console while doing the hands-on, so how the step is very straightforward. Then we also have the custom. So previously we saw the straightforward simple AWS RDS workflow. Now we have this AWS RDS custom workflow. So first we need to connect to the Amazon RDS endpoint. Then we have this Amazon RDS custom, which is a managed database service for applications that require operating system and database customization. It is available currently for the RDS custom for Oracle and RDS custom for SQL Server. Then all our AWS services are deployed into our AWS account. For example, we also have other supporting services like EC2, S3, Systems Manager, EBS. Then we can handle the support parameter, which can monitor and alert on invalid customizations. Then we can install and run legacy, custom and packaged applications. So this is like if you want a very customized solution where you need to, where there are restrictions for enterprises, where you need to follow this version of database and this configuration of database, and you need to store, you need to have that database residing in a specific region. Then to adhere to that compliance and security related aspects, you can go for the RDS custom version as well. AWS has made that option available. So next we can have the features of the AWS RDS. So the first feature is the it is easy to manage. So it is very easy to set up and deploy it. We can set it up using the AWS CLI, which is the command line interface, or via the console, or using the SDK. So we can manage the database administrative tasks. So we can also monitor and view the database metrics. So how we can monitor and view the database metrics is that Amazon RDS in the backend provides Amazon CloudWatch metrics, which is actually a monitoring tool for the database instance at no additional charge. So we can use the Amazon RDS console to view the key operational metrics, including the compute or storage or memory utilization. Uh, it is actually we also get the Amazon RDS performance insight. So that is also a very easy tool actually we can use. Next, we can scale infrastructure with the AWS Cloud Formation. Yeah. So it is actually a Amazon native infrastructure automation tool. So it is a JSON based automation tool. So we can write the code in JSON format, and then we can uh, deploy it using the terminal or in the console. So you can scale the infrastructure accordingly. Again, we have the option to turn on event notifications with subscriptions and Amazon SNS. So we can use the management console or CLI, so that we can subscribe over 40 different database events associated with your database instance. So here Amazon RDS can notify you via the mail or the SMS text messages of database events. Also, it has the enhanced security and compliance with configuration governance. So it can support the compliance and also enhance your security by doing some recording or auditing changes to the configuration of the DB instance. And then we have the database cloning. So Aurora supports cloning operations as well, where we can clone entire like database clusters within the matter of minutes or few minutes actually. So it is very useful like in the field of application development, or if you are doing any updates to the database, or you are running some queries actually. So high availability can also be fostered, since it can also accelerate the software development process as well. Also, it is safer, simpler, faster upgrades with Amazon RDS blue green deployments. So what these blue green deployments help us is they help us to create a staging environment that actually replicates the production environment of your application. So these two environments are always in sync together, which also uses logical replication in the backend. So you can make changes such as major or minor version upgrades, any schema modifications, and also you can do parameter setting changes without impacting the production workload. Next, we can have analyzing the Amazon RDS data using zero ETL integrations with Amazon Redshift. So zero ETL integrations with Amazon Redshift actually it provides access to the analytics and machine learning capabilities on petabytes of your transactional data from your Aurora MySQL compatible edition or PostgreSQL compatible edition. So transactional data is automatically, continuously, and quickly replicated after being written into your Amazon Aurora or Amazon RDS database, and it can be seamlessly made available in the Amazon Redshift. You also have the ability to consolidate data from multiple databases, including Amazon Aurora or Amazon RDS. So this is about how easy to manage RDS is. Next, it has the facility of customizable performance. So the first one is the choice of general purpose and provision IOPS SSD storage options. So actually Amazon SSD, it offers a choice of two storage types. So one is the general RDS general purpose storage that will work for your database workloads. It is a SSD backed storage. It has ability of up to 3000 IOPS above the baseline. Then we have the workloads that require higher performance. In that time we have the provisioned IOPS storage, which is also SSD backed storage. So we have saw these type of SSD storage options in your EBS and EFS session previously. So this delivers fast, predictable and consistent IO performance. IO means input output. Next we can add that as a Amazon Elastic Cache to Amazon RDS databases. So to accelerate the performance of our Amazon RDS database and applications, we can add Amazon Elasticase, which is a in-memory caching service to our database directly from the RDS console. Next, we have the diagnose and resolve performance bottlenecks with Amazon DevOps Guru for RDS. So actually, this Amazon DevOps Guru, it is a cloud operations service which is powered internally by AWS that helps in improving application availability. So popularly, it is used for machine learning related workloads. But for RDS also, it can automatically identify the root cause of performance issues, and also it will give some recommendations so that we can immediately resolve the issue, so that no database experts help is needed. Also, it has improved write throughput with Amazon RDS optimized writes. Also, it has improved query processing with Amazon RDS optimized reads. So next we have the high availability and durability option. So the initial point is we can access point in time recovery with automated backups. So here we have the automated backup feature of Amazon RDS, which enables point in time, means at what point the time we need the recovery, the same state of that database will be recovered for a database instance. So Amazon RDS will back up our database and the transaction logs associated with it, and it will provide both for a user specific retention period. So this allows us to restore our database instance for any second during our retention period up to the last 5 minutes. So maximum days it can be configured is up to 35 days. Also we can perform the user initiated backups with database snapshots. So similar to the EBS snapshots that we saw in the previous sessions, database snapshots also can be taken. So these will be stored in the S3 and will be kept until we delete them. Next, we can achieve high availability with Amazon RDS multi-easy deployments. So this provides the enhanced availability and durability for the database instance, which have a service level agreement of 99.95%. So combined with multiple easy, we can also have cross-region read replicas. So which can increase cross-region means multiple region. replication. So they can increase the resilience and performance by asynchronously replicating data across the regions. Also, we have the usage of Amazon Aurora Global Database for globally distributed applications. So it enables actually fast local rates and quick disaster recovery across the multiple AWS regions from a single Amazon Aurora database. Actually, it is recommended for the and it is also ideal for the globally distributed workloads that have strict availability requirements, such as in the financial, travel, and gaming industries. So in the next slide, we have the security and compliance features. First is the we have the protection of data with encryption and at rest and in transit. So our Amazon RDS allows us to encrypt our databases using keys that we manage through the AWS Key Management Service, which is KMS, which is a native key management service from Amazon. So if we have a database instance running with Amazon RDS encryption, data stored at rest in the underlying storage is encrypted. Also, its automated backups, read replicas, and snapshots are also encrypted. So next we can run the database instances in AWS VPC for network isolation. So what AWS recommends is that we can run our database instances in Amazon VPC, which allows us to isolate the database in our own virtual network and connect it to our on-premise or private data center infrastructure using industry standard encrypted IPsec VPNs. So we can configure firewall settings and control network access to our database instances. Next, we have the control actions of AWS users and groups with resource level permissions. So as we already saw in the IAM section, we can play around with the AWS users and groups with resource level permissions. Next, we have the achieve compliance with key industry compliance programs. So there are many compliance programs. For example, we have HIPAA, we have FedRAMP for US, we have SOC, and we have ISO. So accordingly, you can achieve the compliance with this Amazon RDS. Next, we have the threat detection with Amazon Guard Duty. So it is actually native Amazon solution. So it is available with Amazon Aurora to monitor for the potential threats to our database and workloads. So this is about the security and compliance features. Next we have the high scalability. So in the high scalability, we have the first as power your database with push button compute capability, scalability. So we can scale the compute and memory resources using powering your deployment up or down up to a maximum of we can deploy up to 128 vCPUs and 4096 GB of RAM. So it is a huge scalability option. So actually compute scaling operations typically complete in a few minutes. So within few minutes we can scale up or down our RDS instances. Next we can simply scale our storage. So as our storage requirements grow according to our application needs, we can scale up or down our storage requirements as well. Then we can elastically scale out with Amazon RDS read replicas. So what this read replicas help us is it makes us easier to elastically scale out beyond the capacity constraints of a single DB instance. So we can create one or more replicas of a given source DB instance, and we can serve high volume application read traffic from multiple copies of your data, so thereby increasing aggregate read throughput. Next, we can increase resilience and scalability with Amazon RDS proxy. So this improves database efficiency and make our applications more scalable and secure as well. Also, we can centrally manage our database credentials as well, including the AWS Secret Manager and AWS IAM. Also, it can auto scale with Aurora Serverless version 2. So it's a serverless is a configuration for Aurora that is on demand and provides auto scaling capabilities. Next, AWS RDS is also cost effective, so has most of the offerings. It is pay only for what use. So whatever the configuration we are using, we should pay only for the required amount. Also, we have the capability to receive significant discounts using RDS reserved instances. So if you use their plan accordingly, we can get some discounts as well. So we can stop and start database instances. So we also have that option similar to the EC2 instances. We can improve price performance and predictability at scale with Aurora IO Optimize. So using this option, we can improve both the performance and predict the usage of our Aurora devices. Also, you can start building with the AWS free tier. So we have that option in free tier to use this database instances. Also, we have the choice of commercial licensing options. Next, we can integrate with a modern AI and ML workloads. Also, it has a variety of choice of deployment environments. For example, you can easily manage the database needs as a fully managed cloud database service. So no, you if you don't want to manage all the overhead, then you can use this RDS as a managed service as well. And also you can gain the privileged access with Amazon RDS custom. So there are flexible migration options as well. We can perform homogeneous and heterogeneous migrations with AWS DMS. Then we can migrate using familiar native tools. So we'll be having question, which relational database engine versions does Amazon RDS support? So it has most of the industry leading database support. First is the Amazon Aurora, which is the native AWS service. Then we have Amazon RDS for PostgreSQL. We have Amazon RDS for MySQL. We have Amazon RDS for MariaDB. So we have Amazon RDS for SQL Server, Amazon RDS for Oracle, and Amazon RDS for DB2. So all the primary databases available in the market are taken care of. So next, coming to Aurora, we have the Amazon Aurora. So Amazon Aurora is a fully managed relational database service provided by Amazon Web Services. So it is designed to offer high performance, reliability and scalability, and it is compatible with MySQL and PostgreSQL. So Amazon Aurora is often referred to as cloud native database as it is optimized for using cloud environments. So it is optimized for use in the AWS itself, not in like on-prem or private data center environments, since it is built by the Amazon Web Services company. So here are some key features and characteristics of Amazon Aurora. First one is the compatibility. So Amazon Aurora is compatible with MySQL and PostgreSQL, which are, I think these are the two most popular database options out there, which means that applications using these database engines can be easily migrated to Aurora with minimal changes. So if I already existing application hosted on this, then coming to Aurora is just with like a cake on a walk, like walk on a cake, you can say. Next is the performance. Amazon Aurora is known for its high performance. So it, since it's already built for the cloud, it uses a distributed fault tolerant architecture. Fault tolerant means it has the capability to be hosted in multiple regions across the world. So if one region comes down, there is always availability of next region. So that allows it to be provide very fast and consistent performance. So there is also provision of RAID replicas. Aurora allows you to create up to 15 RAID replicas to offload read traffic from the primary database enhancing read scalability. Replica is nothing but having another copy of our machine somewhere in some another region. So it also has most of the so obviously like has all the cloud solutions already and services that have this feature. It has already high availability. Next it has the backups and snapshots, so similar to the S3 and EBS and EC2 services that we already saw. It has the provisioning of snapshots as well and backup, so automatically we can take the backup of that RDS instance or Aurora instance. Then we also have the security aspect. So as Aurora supports encryption and trust using AWS key management service. Also the data is encrypted in transit using the secure socket layer or the transport layer security protocols. Next we all this have this native integration with AWS IAM for managing access to Aurora resources. So we can configure like different teams. We may be having the database admin teams or the DevOps teams. We can accordingly configure the related access permissions to their RDS instances. Then we have the concept of the global databases. So Aurora global databases enable replication across multiple regions, allowing you to build globally distributed low latency applications. So like we can design the architecture of the application accordingly that we can list these RDS instances in regions where their users are located for uh, having that low latency access in their applications. Next we have the compatibility mode. Aurora supports a compatibility mode for MySQL that allows you to use Aurora as a drop-in replacement for MySQL, taking advantage of Aurora's benefits without requiring modifications to your existing MySQL applications. So it's like a lift and shift type of migration that you can do. So if you already have your application with MySQL, then you can easily transfer that to Aurora based in by moving to the AWS. So we'll just go to the reading mode for better view. Yeah, we have come to the reading view for better viewing experience. Next we have the Aurora workflow. So it's already highly scalable, high performance applications, including those built on modern serverless architecture. Serverless means in the backend everything is managed, so no teams are managing the servers, physical servers in a physical manner. Next we have the Amazon Aurora, which is a MySQL and PostgreSQL compatible database built for the cloud. So this performs all these features like we can configure all like high performance and multi-age availability, flexible and auto scaling compute, low latency cross region application. So in the console we will show like we all have this flexibility to configure accordingly all the key features. Then accordingly we can integrate with other AWS services to perform analytics and extract insights or monitor trends and logs for enhanced security. So these are the like what we can say, these are integrated features. So it is integrated with the Amazon S3, AWS Backup, Amazon DevOps Guru, CloudTrail, Redshift, GuardDuty, CloudWatch, SageMaker, Comprehend, Lambda, which is a serverless offering, EKS is Kubernetes based orchestrator, which is called the Elastic Kubernetes service. So also we can do security credentials management using the AWS Secrets Manager. For example, if you have some key value pairs that are like configured as secrets, you can manage them using the Secrets Manager. So at last we have this DynamoDB. So DynamoDB is also fully managed NoSQL database service which is provided by the Amazon Web Services. So it is designed for high performance, low latency and seamless scalability, making it suitable for a wide range of applications with varying data access patterns. Actually, it's a very super efficient and magically expandable and globally accessible service actually. So it's designed to handle large amounts of data with very incredible speeds, making it a go-to solution for applications that need very fast and reliable access to information. So it's basically a NoSQL database, which is not only SQL database, which means it's not based on the traditional relational database model. It provides flexible schema design, making it well suited for handling diverse and evolving data structures. So it's not very like for example schema means we have a key value pair or a table row pair. So it's not like fixed to a single schema. It provides a very flexible schema based on the diverse needs. Also, it can support both key value and document store. So DynamoDB supports both key value and document data models. Each item in the database is uniquely identified by a primary key, and items can contain attributes of different types. So next, it's a fully managed service. So AWS takes care of the operational aspects such as hardware provisioning, setup, configuration, and maintenance. Users can focus on application development without worrying about database administration tasks. So for example, in most enterprise teams who are having their own data center, we can heard of roles as a DBA. So we have a database administrator. So but if you take care of this Amazon DynamoDB, you can go to the fully managed service where everything, all read and write operations, all querying operations are being taken care of by AWS in the backend. You just focus on the application logic. Next, we have the scalability. So DynamoDB is designed for seamless and automatic scalability. It can handle massive amounts of data and traffic by automatically distributing data across multiple servers. It also supports horizontal scaling. So users can scale read and write capacity independently. Horizontal means more instances side by side instead of vertically scaling. So vertical scaling involves moving the specifications, so increasing the RAM, increasing the storage, increasing the compute capacity, the vCPUs. But here horizontal scaling means just increasing the number of instances. Like if you have one instance, you can increase it to 2, 300, maybe thousands. So it's like called horizontal scaling. Next we have the performance. So DynamoDB provides low latency access to data, making it suitable for applications with real-time requirements. Real-time are mostly means this which have this instant data related like social media applications where you are putting your personal data or credentials. So it is more suitable for those kind of applications. Next we have the SSD storage option. So data is stored on a high performance SSD storage, thereby having high throughput and high IOPS operations. Next we have the consistency models. So DynamoDB supports two consistency models, eventually consistent reads and strongly consistent reads. Users can choose the consistency model based on their application's requirements. Next we have this AWS integration. So being a AWS native service, it supports most of the prime AWS services like Lambda, IAM, CloudWatch and much more, like even S3 and other services. Next we have security. So security is inbuilt into it. As we already saw, it supports AWS KMS. Also it has fine-grained access control with IAM. Also it has on-demand capacity mode. So in addition to the provision capacity, DynamoDB offers an on-demand capacity mode, whereas users pay per request rather than pre-allotting capacity. Next we have the backup and restore. In case any unforeseen circumstances happen, then we can have the automated and on-demand backups as well as ability to restore at any point in time. So whatever the data is lost at that particular time, those instances can be recorded up with the specific retention period. Next we have the time to live. So DynamoDB supports time to live. allowing users to automatically expire items based on a specific timestamp. So this is an overview of how a DynamoDB transaction. We just have an API interacting with the DynamoDB, and the DynamoDB is then interacting with the respective DynamoDB table. So if you are interacting with an API like for example AWS SDK or AWS CLI, so the backend service initializes the AWS SDK with the necessary credentials and configuration to interact with DynamoDB. Then we have a start transaction method happening. So the backend service starts a new transaction using the transact write items operation in the DynamoDB API. Then we can define the transaction operations. So within the transaction, the backend service defines a set of write operations such as put item, update item, or delete item that should be part of the operation. Then each operation is specified as a separate item in the transact items list. Then the another step which happens is execute transaction. So then the backend server sends the transact write items request to the DynamoDB containing the defined operations. Then DynamoDB executes the operations automatically. Then next it will handle the results. So the backend service that receives the result of the transaction. If any operation within the transaction fails, then DynamoDB rolls back all the changes, ensuring the atomicity. So using the DynamoDB API for transactions allows developers to ensure consistency of data even when multiple operations need to be executed together. So it's especially useful when maintaining the integrity of the data is critical and changes need to be applied atomically. So we can see these are some of the services like how much hours is free for 12 months for the AWS free tier account that we are using currently. We can see that Amazon EC2 has 750 hours of free usage per year. Then we have S3 which is 5 GB of standard storage can be used for 12 months free. Then we have the Amazon RDS which is again equivalent to EC2. So we can use around 750 hours of that time. But it says per month of db.t2.micro database usage, so not for other capacities. Next we have the free tier Amazon DynamoDB. 25 GB of storage can be used, which is always free. So there's no like 12 months time limit set, so it's always free across lifetime. Then we have the machine learning. So for machine learning and Lambda, we have 1 million free requests per month, and then we have 250 hours free trial. So this was about the free tier usage. So this was all about the theory. Then we'll go into the hands-on. We'll first see the overview of a RDS and we'll spin up a RDS instance. So I'll go to the AWS console first. Let me sign in into the console. So let me type the root user email address. So let me pause this, I'll re-log in again. So now we have entered the console now successfully. Similar to how we navigated through the other services like EC2, we had AWS backup, EFS, IMS3. So similarly we have to type RDS. So here we'll get the managed relational database service. We need to click upon it. So here we'll get the overview and the UI of all the things. We have the dashboard, we have the databases, query editor, performance insights, snapshots, and all other like subnet groups. Since we haven't created any, so we'll not see any dashboard related information. So first we also have this pop-up saying Amazon Aurora's IO optimized is a new cluster storage configuration that offers predictable pricing for all applications and improved price performance with up to 40%. So Amazon always throws you some kind of like offers or something so that you are keeping updated with the latest trends. So they also say that try the new Amazon RDS multi-easy deployment option for MySQL and PostgreSQL. So they always have this pop-ups. You can always click this learn more and learn any new implementations they have for. So we'll try and create our first RDS database here. So we'll go ahead and click create database. We are already in the US East 1 region, as you can see. Uh, the moment we hit create database, then we have two options. One is the standard create option and another one is the easy create option. But for now we'll go ahead with the standard create, where we have like we'll get a fine-grained control of how to set. So next we have the database engine options. So if you are having some production ready applications, then the go-to and recommended one is the Aurora, which is already managed by Amazon. So similarly we have different types of database engine options. We have MySQL, we have Aurora, we have MariaDB, we have PostgreSQL, we have Oracle, we have Microsoft SQL Server, we have IBM DB2. So all the popular version of database options is available here. So appropriately I'll select the MySQL for now. So here once we click the database related option, so it says MySQL SCS. It gives some details and bits of info which is helpful if you are spinning it for the first time. It says it supports up to 15 read replicas per instance within a single region or 5 read replicas across cross region. So yeah, for now I have selected MySQL. So coming down here, we'll ignore the two filters here. Next we have the version of the engine, MySQL engine. So if you select this, we have a lot of engines here, like spanning from 5.7 up to 8. So but it's always good to select the latest version unless you have any specific requirements. So I'll go ahead and select 8.0.35. Then next we have the templates option here. So there are three options. One is for production, we have dev or test or free tier. So we'll not be provisioning a production template instance here because of the costs involved. It's really high. So we'll just provision a free tier one, but I'll be just showing what are the options involved. So the primary is the availability and durability. So you'll get a super high available, means you can deploy the multi-AZ DB cluster, means multi availability zone. So if one availability zone goes down, then there's already another availability zone available. So the cluster is already spinned up there as well. Next we have the multi-AZ DB instance. So it creates a primary DB instance and a standby DB instance in a different AZ. So if you have, it's for the failure related things. So if you have one availability zone down, then you can provision a alternate availability zone instance. And next is the single DB instance, which creates a single DB instance with no standby DB instance. So there's only one instance here, so you don't have any other instance to make your failover operations. Just walk you through the other options as well. So first we need to give the DB cluster identifier, which should be our database name. For now we have this default as database one, which is already being populated by AWS. Next we have the credential settings, which is the master username. So admin is the default one. So we have also, if you check this, we can also manage the master credentials in AWS using the secrets manager if you have any credentials. For now I'll not check that. Also you can have the option to auto generate a password. So I'll just auto generate a password to log in into that master user for the DB cluster. Then we have the storage classes different. We have the standard class and a memory optimized class. So for now I'll keep the standard class. So it says 4 vCPUs, 16 GB RAM, network is 4750 MB per second, 150 GB instance. So we also have the different storage types. We have the provisioned IOPS SSD IO1 selected by default. So the allocated storage is also 400 GB. The provisioned IOPS is 3000 IOPS. Next we have the connectivity related configuration. So we have like don't connect to an EC2 compute resource, connect to an EC2 compute resource. So I'll let it as it is as the default. So also we have the VPC related configuration. Next we have the DB subnet group. So I'll leave it to default as well. Next is the public access one. So this is a very important one unless you have a very good reason to have that database to be publicly open to the internet across the world. So we should not select that as is. So always we need to have it as a privately accessible database. So next we also have the VPC security group. So we can choose existing. So if I already have one, I think, yeah, just uncheck this and have this already created launch wizard one. So we will ignore everything for now. The retention period is 7 days as per free tier. So yeah, this is the main thing. Just I wanted to show how much cost it is estimated to be for a monthly if you want to run it monthly. So there is around $2000 per month approximately. So 2000 in case I think 80 into 2000 will get you somewhere around 1,60,000, which is very expensive. So I just wanted to show you like if you want to run a production MySQL or RDBMS, then how much it would take. So yeah, we'll ignore all the options for now and just go ahead and create a free tier one. I'll just select the free tier. So you'll see automatically the availability and durability section is gone here. So since it's not supported for the free tier related operations. So we'll go ahead and spin up a new RDS free tier instance. Just select the given name. So you can also configure your name accordingly if you want. Or let us just give it as internship studio database instance. Then I have set the credentials to auto generate a password. So it is db.t3.micro, which is according to the free tier. It is the having 1 GB RAM and 2 vCPUs with network bandwidth of 2085 MB per second. So it's just we'll use a general purpose SSD. So the allocated storage is 20 GB since the minimum value itself is 20 GB. So we'll always leave all the values as default. Again, the subnet group is default, the public access is not enabled. Then we have the VPC security group. Firewall has choose existing. So I have selected the existing launch wizard one which I already created. So availability zone I'll give it as US East 1A. Rest all the things will ignore. Now you can see the price is significantly reduced. It's just $14.71 USD. So $12.41 is for the United States dollars is in the database instance, and storage it's just costing us $2.30. So don't worry, it's not going to be charged to a credit card or debit card. It's just well under the free tier limits. So we'll just go ahead and create the database. So just cancel this. Yeah, while creating it, just got a pop-up. It says these are just the suggested add-ons for internship studio database instance. So Amazon is just giving us a heads up of what to create, like create an elastic cache cluster from RDS using your DB settings you can save up to. So these are just suggestions. So I'll just ignore this for now. So it says creating. It also says consider creating a blue-green deployment to minimize downtime. You can see that our first database is getting created. The status is still under creating. So you can see the region and availability zone. It's being spinned up in the US East 1A. The engine is MySQL community based version. Maintenance is none. I think it will take couple of minutes to spin up. So you need to hit keep refreshing to get the status here. So also have the actions button here to delete it, to stop it temporarily, convert to multi-AZ deployment, reboot, set up EC2 connection, set up Lambda connection, create RAID replicas, to create a blue-green deployment. So we have a hell lot of options here. We can migrate a snapshot as well. We can restore it from S3. Now you can see that it is successfully created. uh, RDS has generated your, it says RDS has generated your master password during the database creation. It will be displayed in the connection details. The only way to view your master password is to choose the view connection details. So if I hit the view connection details, I have this master username admin and master password. So this is only, it says a warning that this is the only time you can use this password, and copy and save the password for your reference. If you lose the password, you must modify your database to change it. So this is a one-time scenario. So please be careful that you need copy it somewhere locally securely and use this. So if I do this cross one times, I'll not be able to see that. So you can just ignore it. So I'll just refresh it once. So it's already getting backed up. So I can see that it's getting a backup to. So now we can see, like after some 1 or 2 minutes after it has backed up, so we can see that the status is available. So once that status is available, you can do a lot of actions. So earlier you can see these were blurred up and were not available. So we can have, like, we can stop it temporarily, we can reboot it, we can delete was already available. So we can set up EC2 connection, we can create a RAID replica, we can take a snapshot. So I want to know the details here, so I'll click it here. So you can see the CPU percentage, so how much it is utilized. We can see the class, we can see the engine again. So a lot of connectivity and security details. The port is 3306 for SQL. So we can have the subnets it is under in. So I can have the monitoring details here with the CloudWatch. So every 5 minutes it's an interval it is being monitored. We can have different parameters like bin log, disk usage, burst balance, CPU credit balance. So you can also see the tags. We have the maintenance and backups. So auto minor version upgrade is enabled here. So this was about the database spin up thing. So congratulations, you have learned how to spin up your AWS RDS database instance. So I'll just go ahead and delete the instance so that I'll save up some money. Oh, it says permanently delete internship studio database instance, DB instance. You can't undo this action, means you can't revert this action. So AWS always has this for any service that you spin up. It says, it gives a warning and you can always confirm it twice so that if you can go ahead and delete. So to confirm deletion, it says type delete me. So yeah, I'll go ahead and delete it. It says the status is deleting DB instance. Just hit refresh. It takes a couple of minutes always. It's not always dependent on your internet connection or whatever. Just be patient that it's in the backend that server is getting terminated, since all operate in the cloud via the API, so it will take some time to be updated in your browser. So now you can see after around 3 or 4 minutes, uh, actually the DB instance got deleted. So what we'll do is, so we'll implement something called read replicas. We'll create a read replica. So what read replica is will do is they actually enhance the read performance of the intensive applications. So if you have applications who involve very high intensive read or write performance and operations, then you can implement something called as read replicas. So for that, first we need to create a database. What I'll do is I'll again create a fresh database out of MySQL. So I think all the operations will be same as earlier. I'll just go for free tier. Then again database one, will keep the name as it is, database one. Auto generate a password again. So all the configuration would be same. Then left zone preference, again I'll go 1A. Then we'll go ahead and just create this database again. I think I'll hide add-ins for 30 days. So it will again take around 2 or 3 minutes. So now as you can see, the status is available. What I'll do is I'll select the RDS instance. Under actions, I'll just create a read replica. So we get the settings option here. So the source, the replica source will be what we have created, the DB instance name. So in our case, it is the database one. So next we have the DBS identifier. So this you can use as an identifier, like by what name you can call it. For now, I'll just type DB replica, since we are creating a replica here. You can use any of the identifiers, like for example, if you are using it in an enterprise environment for like production replica or development replica or testing replica, you can name it accordingly according to your needs. Next we have the instance configuration. So what types of storage classes to use, whether we need a standard class or memory optimized class or burstable classes. So we'll start creating a read replica. So we'll just go ahead with the burstable classes since it is part of a free tier anyway. So it includes the T classes. So we have this T3 micro, which suits us as according to our free tier version. So again in the destination region, since we already have the instance in North Virginia, which is US East, I'll go ahead and select somewhere in Tokyo. So it's upon the design considerations again. So you can use either from according to application needs where your replicas need to be. So we have a lot of region availability. Apart from Japan, we have European Union like London, Paris, Stockholm. So what I'll do is I'll just spin up a replica in Tokyo. I'll just select Asia Pacific. So yeah, right. So I'll just select the storage type as it is. I'll leave it to defaults. I'll just leave the availability. I don't want to select a multi-AZ DB instance, so I'll just go ahead with the single DB instance. So IPv4 also, we'll select IPv4 here. DB subnet group is none again. So availability zone also will not, leave it as default, no preference. So password authentication is required. Again, there are some options for backup, encryption. So leave as it is everything. Just go ahead and create a read replica. Oh, sorry, I think. So I'm using all the details as it is. And just go ahead and create a read replica. This will take time actually. It says modifying and creating replica. So if I go ahead in the Tokyo region, so let me go to Asia Pacific Tokyo AP Northeast 1. You can see a replica being created. So we'll wait for some time to get it created. So we'll keep on hitting refresh until the status becomes as available. I'll just go to US East 1 region again to see where my database is up to. It's still under modification status, since it's creating a replica out of this source instance. So let us try to keep refreshing. We can see our primary instance has come up available. So I'll quickly go to the Japan region, which is in Tokyo. It still says the replica is creating. Let's wait for some more time. So we can see that after around 10 minutes, 10 long minutes, you can see the read replica is finally ready. So it takes significant amount of time. So be patient, like while it is getting in the refresh state. So let me just go into the North Virginia region. So if you can click here and see that there's a replica already available here. So you can see under the DB identifier. So it is the primary one, and the DB replica is based in Tokyo, and the role is a replica here. So the details is populated under the replication section. And once again, I'll go to the Tokyo region, and also we can promote this replica. So we have that option here. So just go to under databases. So if I click here and under actions, we have the option to promote this as an independent RDS instance. So I'll go ahead and promote this and go ahead and promote the read replica. So yes, this was about the hands-on session related to the Amazon RDS. So now what we'll do is we'll go ahead and create our first DynamoDB table. So just show it's a managed NoSQL database. So this is the first time it says that it's the UI of the DynamoDB. It says it's a fully managed key value and document database that delivers single digit millisecond performance at scale. So here we have the pricing, documentation, benefits and features, and other use cases as well. So let's create a first table. So I'll give a table name. Let's give internship studio table. Give the partition key name. I'll give as something as DB name. It will be a string, and DB value. It will be as just also the string here. So I'll keep the table settings as default. The table class will be DynamoDB standard. Capacity mode is provision. Provision rate capacity is 5 RCU. Provision rate capacity is 5 RCU. Auto scaling is on. So we'll just go ahead and create the table. So it's almost instantaneous, as you can see. Our table is created here. So it says it's available for use shortly, but it's already can say that the status is active. You can go inside the table. You can see that since we haven't added any items inside it, it says 0. So it's just an overview that I have given, and you can play around with it. So yeah, this was all about the hands-on session. Let's jump back to the slides. Hope you had a productive session. So quickly we'll wrap up. So we'll just talk about the best practices. So these are the database best practices that you have to keep in mind before playing around with the database related services. First one is choose the right database service. So always select the database service that best aligns with your application requirements. So AWS provides a variety of managed database services including RDS, DynamoDB, Aurora, and more, each tailored for specific use cases. So you should right size and monitor the resources. So regularly monitor performance of your database instances and adjust resource allocations based on usage patterns. So use AWS CloudWatch or other monitoring tools to track key metrics. So you should implement high availability for mission critical applications. Always leverage the high availability feature. Next, also use backup and restore strategies. So establish regular backup schedules for your databases so that in case of any mishappenings, you can always revert back to the original situation. Next is we can enable encryption. So also for data transfer related things or database related things, you also always see that you enable encryption using the native AWS key management service. Also always use IAM for access control. Use the principle of least privilege always for all operations. Also implement network security. You can leverage the network security by leveraging security groups and network access control lists. So we'll see what in depth of all these things in our next section, which is the AWS networking session. So always secure data in transit. So we should enable the SSL or TLS for encrypted communication. Also, as we previously saw, always monitor and analyze performance of the database systems. Implement the disaster recovery plans. Always look for going for multi-AZ solutions or multi-region solutions. Always look to deploy multi-availability zones. Also stay informed about updates. Always be on the check of what AWS is looking for and follow their documentation regularly if they are having some security updates or any machine related updates so that you can go ahead and quickly fix those. So always be aware about the cost optimization techniques as well. Always optimize cost by selecting the appropriate instance types based on your workloads. Also take help of their Aurora serverless and DynamoDB on DB capacity. So thank you for attending the session. Hope you had a productive session. So in a summary we saw what are the AWS databases. So we saw from scratch what a database is, what is the workflow of a database, what are the different types of databases, and we actually primarily focused on RDS, Aurora and DynamoDB since they are widely used in the industry. So we also saw hands-on on how to create a Amazon RDS database. Also we saw how to create a RAID replica of a Amazon RDC database. We also saw how to create a sample DynamoDB table. We also did hands-on session on also saw the best practices. Hope you understood a basics of AWS databases. In the next session, we'll be covering a wide variety of AWS networking services available. We'll see what is VPC, what are subnets, what are security groups. We'll do a VPC peering. We'll also see what is transit gateway and its types and advantages. So see you in the next session. Bye and thank you for attending.